All right, we are happy to have Norihiro Iizuka talking about Krylov complexity as an order parameter.
Okay, thank you very much. So first of all, I want to thanks to the organizer for inviting me to this wonderful workshop. And it's always nice to be back to India. I just one announcement. I just recently moved from Osaka to Taiwan. But I'm also affiliated to the Yukawa Institute. So if you come to Japan, also you can meet me. Okay, so I want to first thanks to my collaborator. I talk basically on the work recently I have done with these two young generation of the people from Japan. They are actually Osaka PhD student. And but the model itself is actually I have done with Joe long time ago. Okay, so that's the stuff. Okay, so I want to first summarize my talk just in case you sleep or you just disappear for the coffee. Okay, so what's the summary? I will talk very simple large quantum mechanical model, okay, which we call the IP model. I have a bit hesitation to call it IP because it's a name of us, but my excuse is that Joe called it as an IP model, so I have an excuse to use the IP model. Okay, so I explain what is the model, and then that is introduced as a toy model for the black hole in ADS. Now, this model shows some nice feature. These are all the stuff. Key feature of the summarization and information loss. But the new stuff is that we solve this system in the large N and at high temperature. And then we study new quantity called the Krylov complexity. And then, nicely, this Krylov complexity show exponential growth in time. Now you may wonder why this is important. Now there's a conjecture that if Krylov complexity grow exponentially in time, it's an indication of the some nature of the chaos. So since our model is originally motivated for the black hole, it's nice that this model show chaotic nature as well. And as I know, I look at the literature, this is the first example found Krylov complexity show exponential growth in time in large N quantum mechanical system. Okay, if you know other example, please let me know. The model show various, the IP model show various spectrum change for the vector field from correction of the delta function to bunch of the branch cut and totally continuous spectrum. The Krylov complexity, what we found is always exponentially growing as the spectrum is continuing. Okay? So given this, we give a prescription to apply this idea to more quantum field theory, but we compactify quantum field theory, goes down to the 0+1 dimensional quantum mechanical system, and then we give some prescription to use Krylov complexity as an order parameter for the confinement, deconfinement transition, motivated by the study of the model. But there's one last punchline, which is a bit unfortunately. Unfortunately, our model of the auto calculation show no exponential growth. So our model has some aspect of the chaotic nature, but not totally satisfactory. Okay, that's a punchline. So there's a warning. I have to apologize in this quantum information conference. Unfortunately, my talk contains no entanglement, no von Neumann algebra, and no JT. So I do a very simple large N quantum mechanics, okay? But don't get me wrong, I'm not saying I'm not interested in this one. I'm interested in, but I'm not able to do it, okay? Okay, so let's start. So the introduction, the model. What is a model? It's a very simple model, okay? I tell you. The main character of the model is just two guys. One free matrix and one vector, and then they couple. And that's it. Okay? Now you may think, why you are interested in such a very simple model? I explain. So this is a part of the free harmonic oscillator for a single large N matrix. Okay? Sometimes I call it a matrix, sometimes I call it as a UN adjoint, but the name doesn't matter. So this is a harmonic oscillator of the adjoint with small m as a mass. This is, as you know, in quantum mechanics, we write it down free harmonic oscillator for a single vector field, or sometimes I call it a fundamental field. As you know, in the quantum mech, we write it down in terms of the number operator. Okay? So these are free, and then we just let them interact through this coupling, and G, we call it as like Yang-Mills coupling. So why this is an interesting model? Let me explain the background. Suppose we have a black hole, and if you're interested in, you want to study the black hole, how do you do it? Well, simply you put the test particle and see how does it move in the gravitational potential. So we do the same, But since I am a bit older generation, instead of putting black hole probe particle, I put a probe deep brain. Okay? In now modern age of the people don't use so much deep brain, but I use it. Now, if you want to understand this in holographic setting, instead of the black hole is made by lots of the deep brain, and they are thermally excited. Okay? So for my purpose, I distinguish N deep brain, which makes a space-time with a black hole as a background deep brain. Okay? Now I put the probe deep brain, which I name it as N+1 element. Okay? Now, because of the open string between them, there is a field which corresponds to the vector field because the label is I to N+1. They play the role of the vector field in the UN representation. Okay? Now, in terms of the N+1 by N+1 matrix label, this is a background matrix correspond to N by N, and these are the vector field which is induced because you put the probe deep brain. Okay? And this N+1 to N+1 element represents the position of the probe. Okay? That's it. So the main character of my game is this N by N matrix and the vector, which is fundamental representation. Okay? And I put the position of the deep brain of the probe very far away from the black hole. So I take this wave to be large. That means the mass of the vector to be large. Now, as you know, if you do the path integration of the open string, due to the open closed duality, that corresponds to the gravity exchange. Okay? So that's it. Now, the motivation, which I studied before with the Joe, is that how the fundamental feels the effect of the black hole, meaning that through the path integration, how does this guy get summarized through the effectively black hole of this guy. Okay? But in order to explain the situation, let me give some definition of the parameter which we consider. The matrix, okay, one big matrix. I call the M as a mass, small m, as a mass for this matrix. Okay? As I said, this guy is forming a black hole. So I said the mass of small m to be the same order as the temperature which I consider. I put the probe a bit away from the black hole, and there is a long open string. Therefore, their mass is proportional to the distance, which I name it as a capital M. So I take capital M to be very large compared with the typical scale of the small m or temperature. Okay? Excuse me. So that's it. So that already gives a motivation for the model. So the model has three elements: a joint for the black hole legs freedom, free, with a small m as a mass. Yeah, there's a temperature here, somehow. So m is the same order as the temperature. Okay? And the vector, which is because of the probe, has a mass which is capital M. And I take capital M to be much, much bigger than small m or temperature. Now interaction time. Because the interaction has a following structure, okay? Because of this structure, we simply take this following index contracted structure. Okay? And then I set the coupling as a G. Okay, that's it. So that's a setting we study. Now the goal is that we want to see how the fundamental information or oscillation keep decaying from usual CFT result, or sorry, from quantum mechanical result into total decay, like Magnusen's idea. So the curious quantity which we want to study is a correlator of the vector, because vector proves the black hole. Okay? So we are focusing on the following observable. It's a time order correlator of the fundamental. You create it at time t prime, and then you annihilate at time t. Okay? So it has this free theory part of the correlator. Now, since this capital M doesn't play much role in our talk, I just shifted this capital M contribution and then write it down the correlator in this way. So omega equals 0 corresponds to the omega equals capital M. And that's it. Now we solve it. What's the Schwinger-Dyson equation? This is a Schwinger-Dyson equation in the large N. So the rest propagator equal free propagator, and because of this coupling, we have this construction. Okay? Now we have one loop by the adjoint. Okay? There's a color index N. So there's a fixed soft coupling, and then in planar limit, this is it. Okay? So it's very simple. In terms of the equation, this is the equation. Now, unfortunately, this is a quantum mechanical system. It involves the integration. And it's not that easy. But before that, let me explain what is a propagator for the adjoint. Propagator for the adjoint is free one, but since I take the mass of the adjoint to be the same order as the temperature, this is a propagator for the adjoint, which is free. Now, I should mention that even though a joint feels the temperature, okay, the pole of the joint is still discrete. Okay? Even though you have the final temperature effect, the pole is still discrete and real.
Okay? Adjoint propagator is not corrected at reading order.
Reading order is 1, 1. There's a correction, but that's suppressed by 1, 1. So we want to solve this system. Again, small m is for the mass of the joint, and then capital M for the vector. Now, obviously, the spectrum is discrete if G is 0. Now, how does a discrete spectrum system show an interesting spectrum in the large N? And that's a question. Okay? And again, I always consider capital M to be very large, implies the probe is very far away from the black hole. Okay, we solve it. Okay, I don't know how to solve it. In zero temperature, we can solve by hand. The correlator has this structure. This is a correlator for the vector. And then as you can see, there's an infinite number of the zero in the denominator. So meaning this is the infinite poles, which is set by the zero of the denominator. So the spectrum at zero temperature is, okay, this is numerical, so we cannot write down infinite amount of the delta function. The spectrum for the vector has infinite amount of the delta function. Okay. So that's the result in Toft coupling limit in non-zero Toft, large N, and zero temperature. Okay. Now again, I say if G is 0, lambda is 0, spectrum is discrete. Even we take into account Toft coupling, still at zero temperature, spectrum is discrete. Now we increase the temperature. And then how does the system decay? So I tell you the result. The zero temperature discrete pole, actually once you increase even tiny amount of the temperature, spread into tiny branch cut. Okay? So you can see that the delta function actually spread as a cuts. Since we have infinite number of the delta function, there's an infinite number of the cuts, and then there's a gap in between.
Sorry, at low temperature, the mass of the fundamental is renormalized.
Mass of the fundamental is renormalized.
Zero temperature.
No.
So the self-energy kind of bubble doesn't do anything.
Let's see. Are you asking the vector or adjoint? Which one?
Vector.
Vector, yes. So the diagram which contributes in the large N is the one which I did. And that's it. Is a Shinga-Dyson equation which I showed. Yeah. And that's it. Any more connection?
That looks like a self-energy.
Yes. So that's why the spectrum changing.
So this self-energy correction, is this just accounted for by renormalizing the mass?
Or I would say the spectral density, how does it change?
So it's a function of omega, so it's complicated.
Yes, exactly. So that's what I'm showing.
Right.
Just to make sure, so you are at zero temperature, if you turn on the Toft coupling, the poles will shift.
Shift, exactly.
But they are poles.
Exactly. So you are right.
But they shift in a more complicated manner than just changing the mass.
By changing the temperature.
No, just zero temperature.
Oh, in zero temperature, yes.
Stick to zero temperature.
Okay.
It's not some new effective mass. It's more complicated.
It's more complicated, yes. So let me say more precisely. In zero temperature, let's talk everything zero temperature. If coupling is totally zero, you have only pole in zero. Meaning that omega is capital. Yeah, infinite harmonic oscillator with the same mass.
Yeah.
Now you turn the Toft coupling, again zero temperature, it's become very complicated correction of the pole. That's it. And then the position of the pole is analytical, you can solve it, and then that's determined by the denominator here. So it's a very complicated system. Okay? So this is the result in zero temperature. Now you make the temperature bigger and bigger, so G's cut keeps spreading, and then bigger and bigger, and then they merge, and then become totally continuum spectrum. Okay? So it's quite notable to me. And there's a critical temperature where the gap is totally filled, and then it's become totally continuum spectrum, which we sometimes call the TC. And that's a non-trivial function of the system. Anyway, there's a critical temperature. So in zero temperature, it's a correction of the delta function, and then they keep spreading, and then at some critical point, all of them merge, and then become totally gapless continuum spectrum. All right, so then that's what we did a long time ago. That's it. Once we have a totally continuum gapless spectrum, if it is a Fourier transformation, because of the continuum spectrum, correlator keep decaying, and then it's an indication of the information loss. It's actually exponential decay. Okay, so let me go to. So that's a motivation. Now we want to study the Krylov complexity for this vector field. Now I won't say much about the Krylov complexity, but I just say the definition. Whatever operator you have, how does the evolving quantum mechanical system is you sandwich by e to the IHT. please.
So just finite temperature, if you look at this 2-point function, it decays. Now, like a Pawel or exponential?
Exponential decay.
Exponential?
Yeah. Yeah, this is a quasi-normal mode. So what we expect is that in complex frequency space, the pole become cut, and then once they merge, and then go below the complex frequency space, and then become quasi-normal mode, which contains the imaginary part. So now I go to the Krylov complexity. Now I don't say much about the Krylov complexity, I just give the definition. Whatever operator you have, you sandwich by the commutator of the H, and then you keep obtaining new and new operator. But these are not necessarily orthonormal each other. You modify it into orthonormal each other by defining your inner product, and then you can do it. There's a straightforward algorithm to do it. Now, Krylov complexity is simply whatever operator you have, you let it evolve into time, and then given this time evolved new orthonormal basis space, you expand. Okay? Now, how much this coefficient keep growing is our interest. Now, one proposal is that we disarm this guy by giving the weight increasing 1 whenever you obtain new operator, and then that's a quantity called the Krylov complexity. And that's it. Yeah, whatever operator in quantum mechanical system, you can calculate. Now, why I'm interested in this one? Well, simply because there's an old paper by Parrikar et al., and then they claim that if you study Krylov complexity in quantum mechanical system, and suppose it grows exponentially in time, the claim is that it's an indication of the chaotic system. Now, whether this is completely true or not, what is the current status, I'm not so much familiar with, but this is a motivation. I want to study yes.
Sorry, Nori, when you expanded your operator O of t in some basis,
Yeah, so there's a straightforward definition called the Lanchos algorithm. Whenever you have the operator, you evolve, so you have the zeroth operator, t equals 0, and the next operator is essentially obtained by commutator with h, that gives a new operator, but make it to be orthonormal. And then new operator is again takes the commutator with it. It's a straightforward fixed method. So that's the motivation. It's a really chaotic over our model. I mean, from this new viewpoint. And that gives a motivation to study this old model and study what is a Krylov complexity. Now, there's one evidence. Suppose you consider SYK, but it's a large Q. You can analytically show that Krylov complexity grows exponentially in time.
So if you read like the Susskind papers in the holographic black hole complexity increases linearly, is that equivalent to Krylov complexity increasing exponentially? What's the correction?
I should know, but I don't know. Okay. Sorry. Any other question? So obviously in our model, only non-trivial dynamics is vector because our joint is free. So we want to see how this guy keep growing, and then in this prescription, what is the Krylov complexity? Very simple, it's straightforward. Again, in zero temperature, because we solve the green function analytically, we can obtain what is the Krylov basis analytically, and then we can obtain Krylov complexity analytically in zero temperature. As I showed, green function is very complicated. Pole is given by denominator of the complicated Western function, so it's very non-trivial. But what we can understand is intuitively, this is a Krylov basis, and you can understand easily. You excite from the vacuum, fundamental. Since fundamental is very heavy, you cannot excite two fundamental. But as I say, adjoint mass small m is light with the order of the temperature. So there's a bunch of the adjoint is accompanied with the fundamental. And these are the Krylov basis. In the Krylov basis, operator keeps spreading, and that's it. Now we can calculate the Krylov complexity at zero temperature, and then it doesn't decay at all, and that should be, because it's just correction of the delta function. Green function doesn't decay, it's just oscillatory. So is Krylov complexity. Our interest is the high temperature, where green function decay, but to show that, we just do the one calculation from the green function. Once we obtain the green function from its real part or imaginary part, you can obtain the spectral density. Half time, now, okay? Then from the Schwinger-Dyson equation, we can rewrite the Schwinger-Dyson equation in this way. Now, once you obtain this equation, it's easy to show that at large frequency limit, the spectrum decay in this way. It's exponential decay. That's what you can show from the Schwinger-Dyson equation. Okay? Now, why this is important? Actually, this is a key nature. The spectrum decay exponentially in large frequency, and then there is no upper bound. And that's important for the Krylov complexity actually grow exponentially in time. So our model at large temperature, Krylov complexity grow exponentially in time. It's not e to the t, it's actually e to the square root t, but that's we can explicitly check.
The spectral density of there is the imaginary. It's the same as rho.
Exactly. Yeah, sorry for convention. Any other question? So actually Krylov complexity grow exponentially, and we can check also numerically that it's grow exponentially. So far so good. The old model we study is very simple one, and as is indicated by the Krylov complexity's work, it shows exponential growth. And as I know, this is the first example which show exponential growth in matrix quantum mechanical model. Okay, nice. But let's continue. How does the Krylov complexity change from zero temperature, which is just oscillatory, to the exponential growth in high temperature? Okay, as I said before, there's a critical temperature where spectrum become totally continuum, and then no upper bound, and then all of the gap disappear. So what we expect in the beginning is that at that critical temperature, Krylov complexity does change. So in between, there's a critical temperature, all of the gap is filled, and then totally continuum. And this is the result. Okay, I won't show the calculation. So the result for it. Low temperature, zero temperature, discrete poles. As we increase the temperature, it's a gap. Pole become cut. But there's an infinite cut, and there's an infinite gap in between. As we increase the temperature beyond the point, critical point, it's become totally gapless continuum spectrum. Okay, that's a behavior. So green function in real-time evolution, in zero temperature is oscillation. If there's a gap, power law decay, continuum spectrum become exponential decay. So exponential decay only above the critical temperature where there's no gap.
Is there a black hole analog of that middle phase?
Middle phase is, we believe this is an artifact of our simple model. This is a black hole phase. Okay. But Krylov complexity show again oscillation, but whenever we have non-zero temperature, it shows exponential growth, and that's the result we obtain. Okay. Why TC is not the critical point to change the critical Krylov complexity? That's a question. Now, but before we go that, and then we can see why this equation is just rewriting the Schwinger-Dyson equation, show there is no upper bound in the spectrum. As I said before, Krylov complexity, in order to show the exponential growth in time, it's important that two facts, excuse me. There is no upper bound in the spectrum, and then in large frequency, the spectrum decay exponentially in frequency. And these are the important points. And if this is satisfied, more or less Krylov complexity show exponential growth in time. So it's important. Why our spectrum has no upper bound? Okay, that you can easily figure out from this Schwinger-Dyson equation. And suppose at some omega, okay, there's a spectrum, but above that, it disappears. Suppose there's upper bound. You can find such a critical omega naught. But then you plug in this equation by setting omega as omega naught plus m, you obtain this equation. Okay? But since we say omega naught is near the upper bound, above that there's no spectrum, you obtain this frequency, but this is zero, but this again is non-zero, so it's obviously in contradiction. Okay? So our structure of the Schwinger-Dyson equation say there's no upper bound. But now you may go back. This structure came from where? I mean, it's important we have this three term. This three term, if you go back to the Schwinger-Dyson equation, it actually comes from this finite temperature piece of the adjoint correlator. You can actually show that with absence of this finite temperature piece, our Schwinger-Dyson equation show only correction of the poles. So it's crucial to have a finite temperature. Now let me go back. This finite temperature piece is very crucial, but where this came from? Okay? As I say, our model is simply adjoint and vector, and then there is no gauge boson. But in many of the holographic models, we have a gauge boson. Okay? Now, gauge boson usually gives a singlet constraint. Okay? But our model, since there is no gauge boson, there is no singlet constraint. But suppose there is a gauge boson. We introduce a gauge boson. How the correlator for the adjoint is modified? Because we introduce a gauge boson, as is well known by Shiraz and the company. If there's a gauge boson, the non-trivial dynamics is determined by the Polyakov loop, which is an integration of the gauge boson A naught along the time direction. And that plays a role of the phase transition, meaning that Fourier group is uniformly distributed at the zero temperature or low temperature, correspond to the confining phase. And in the deconfining phase, they accumulate to a certain point. Since adjoint has a color charge, you get contribution from the Fourier group. As I say, in confining phase, U is uniformly distributed. Suppose you sum over all of the contribution of the Fourier group, they cancel because it's uniformly distributed. So in the end, this non-zero temperature effect is gone. But in the confining phase, since U is accumulated, it gives a contribution corresponding to this temperature effect. So we interpret the effect of this non-zero temperature one is actually effect of the deconfining phase. So that's it. Now let me continue to the Krylov complexity as an order parameter for the confinement deconfinement. So as I told you, our non-zero temperature effect, which is 0 to non-zero, is associated to the deconfining phase where final temperature piece came from the Fourier group is accumulated. Now, I should mention just one point. Our model has a matrix and whose mass I say M is non-zero. Now you may wonder, if M is 0, what's happened? If small m is 0, the mass of the adjoint is 0, the system is totally different. I just mentioned the result. If m is 0, then spectrum becomes simply Wigner. Okay? It's a very boring spectrum. It has an obvious upper bound, and two-point function decay only by power law. And then Krylov complexity doesn't grow exponentially in time. So what we understand from this is that in 0 plus 1 dimensional quantum mechanical system, as the spectrum is continuous and no upper bound, and then tail decay exponentially, Krylov complexity grow exponentially in time. So far we have studied only the toy model in quantum mech. Now we want to understand what we can learn by applying this to the quantum field theory. But again, what we learn is a quantum mech. So in order to apply, we compactify quantum field theory to make it quantum mechanical system. Now, there's a famous work done by Dimarsky and Smolkin that suppose you naively apply Krylov complexity in the quantum field theory, it fails as a diagnostic of the chaos. And the reason is simple. Even in a free scalar quantum field theory or non-compact space, okay, suppose you do the quantum field theory for the free theory. Okay? Free theory is obviously not chaotic at all. Then Krylov complexity actually grows exponentially in time. So in quantum mech, it may be the diagnostic of the chaos, but in quantum field theory, it doesn't work as a diagnostic of the chaos. But the reason is very simple. Suppose you compactify quantum field theory on a circle. Okay? Non-compact limit is a circle of the compactification goes to infinite limit. So there's an infinite number of the massless KK mode. Okay? Because of the infinite number of the massless KK mode, this is a reason why you have a continuous spectrum, and there's a Krylov complexity grow exponentially in time. So we somehow want to remove this artifact of the space non-compactness and then compactify quantum field theory and make it to a quantum mechanical system, which understand completely about the Krylov complexity behavior. So we compactify the space. Then it works. So this is again the work of the Dimarsky and Smolkin. Suppose we consider, say, free scalar field in the S1 cross S3. Now, if S3 size R goes to infinite limit, it's essentially non-compact scalar theory. Okay? In this case, you can show that Krylov complexity grow exponentially in time. But on the other hand, if we make R to be very small, at least smaller than the order of the temperature scale, it reduces the quantum mechanical system. KK tower is discrete enough, and then you can check explicitly Krylov complexity show only oscillatory behavior. So the upshot is very simple. Compactify quantum field theory and make it quantum mechanical system, which we understand kind of complexity behavior very well. Okay? That's it. So this is another example which you consider. This is some toy model. Instead of the S3, technical reason, we make it S1. But we have so much spectrum. Why we consider such a model? Suppose you consider QCD-like theory. In IR, you have an effective theory, but you have infinite number of the ledge structure. In order to take into account, we introduce ledge structure parameter n. The gap is capital small m, sorry. But the width between first guy to the next guy and next guy, that's given by delta m. Whether spectrum is continuum or not is determined by delta m, whether this is big or not. So we want to study when this is small or big, Krylov complexity grow exponentially by removing the continuum momentum coming from the spatial direction. So we just give the prescription. In gen, this all work. I just give the prescription. Take quantum field theory and take the temperature near the phase transition point. That's the first point. And then next, we compactify quantum field theory sufficiently, means that sufficiently small enough compared to the temperature, which is the same as transition temperature, transition scale. And then we remove the continuum massless KK mode. And then we study the Krylov complexity. And then you can confirm that if mass gap is big enough, Krylov complexity doesn't grow exponentially. But if mass gap disappears, Krylov complexity actually grow exponentially in time. So in that aspect, confinement or deconfinement, you can detect by the Krylov complexity's time evolution. And not only this toy model, okay, we study, but we also study several operators of the holographic system. And then we confirm that this all work. So that's a punchline. The main message is that we compactify quantum field theory to make it quantum mechanical system. Then what we understand from the previous model does work. So that's a summary so far. So we study very simple model, and that shows the key nature of the black hole summarization, as well as Krylov complexity grow exponentially in time. Then we study how this model's barrier spectrum does affect to the Krylov complexity. Our conclusion is that as our spectrum has no gap, continuum spectrum, it shows exponential growth. But since our zero or non-zero is like confinement, deconfinement, we guess that this may work as a confinement, deconfinement order parameter. And then it does work, as we have studied, is a larger limit. But there's a one final punchline. We study autox as well, and then it doesn't show exponential growth. That's a final point. So, final point, is our model chaotic? Okay, it shows Krylov complexity exponentially, but we should study autoc now. So this is a pictorial diagram of our model. What we have studied is just upper bound of the diagram. Now, this is actually the graphic unit studied by Festcher Liu. What they show that it's, if there's a non-zero Toft coupling, however small it is in late time, perturbation breakdown. Okay, and that's exactly what you expect for the summarization. Now, what we have studied is just upper part of this model. We have fundamental, and we have adjoint, and that's a graph. Okay, you just make one more copy, and then that's a diagram. On the other hand, SYK is this diagram. This is a melon diagram. Now you may see that these diagrams are very similar. That's a motivation. A second motivation, for the auto calculation, you have to calculate many ladder diagrams. In SYK, these are the ladder diagrams. But in our model, these are the ladder diagram. Okay? Again, to me, structure looks very similar. Okay? Only the difference that in SYK, everything is a fundamental, everything is a fermion. In our model, there is a hierarchy between vector model, vector contribution, and adjoint matrix contribution. Okay?
Just to point out, the first one is exactly the structure you get in Mac-Simon.
Okay.
And that's also not.
Okay, good. So actually, this also studied long time back how the autoc behave in the IP model for the m equals 0 case. Okay? But as I told you, m equals 0 is very different from m non-zero. Because as I told you, m equals 0, spectrum is Wigner, 2-point function doesn't decay exponentially, it's just power of decay, and Krylov complexity doesn't grow exponentially in time. So it's not at all chaotic to me. So m equals 0 doesn't show exponential growth. It's not surprised because somehow we know it. It doesn't show any interesting behavior. Our real interest is that for m non-zero case, which we have studied, is it really true or not? That's a question. And then we studied. I won't show the calculation. I just show the result of the final data. So what is this n? Okay, we have to sum over an infinite number of the ladder diagram. Okay, and in practice, this is very difficult. So we numerically keep summing over many of the ladder diagram, and by increasing the number of the ladder, how the autoc behavior keeps changing. Okay, of course, in later and later time, more and more ladder contribution is important. So this is the result. In small ladder, this is the behavior, but as we increase the number of the ladder, the autoc behavior keep growing, but it doesn't grow exponentially. There is an upper bound. It doesn't go over. Similarly, for other parameter we study, as we increase the number of the ladder, that behavior at late time keep growing, but it doesn't grow forever as exponential. So we have to reach the conclusion, even for non-zero M, the mass of the joint, auto do not grow. Okay, that's very unfortunate. But there's one important point. Okay, as I said, vector field has a non-trivial interaction with a joint because the number is n to n squared. But the adjoint is free, is a leading order. So there's a hierarchy. Now we can set up interesting many matrix model and somehow make it solvable way by introducing a control parameter. But that's some work which will be appear soon, but that's a different direction. So in that sense, because of the hierarchy, IP model show only, I would say, partial summarization in the sense that if we restrict to the space of the Hilbert space where you have the one vector accompanied with a many adjoint, in that space only, they show chaotic behavior. But as a total system, it doesn't show chaotic behavior. And we believe that if the field in the model, if all of the field in our model gets summarized, then auto should grow exponentially. But in our model, vector does, but adjoint doesn't, and that's a difference. So basically, I think that's it for me. So thank you very much.
Questions?
So my first question is can we make a vague analogy of the system to Brownian motion where the vector is like the Brownian particle and the n squared matrix is like the background in which it's moving, so it's getting kicked around?
I think you're right. N square adjoint, which in gen plays a role of the background summer bus.
Yeah.
And then particle is moving in this summer bus is exactly what we are studying.
So basically my question was, if we study, let's say, classical Brownian motion and ask, is there a classical Lyapunov exponent in the system? Do you know the answer? So it's not directly related to your talk, but.
I don't know.
Okay.
I should know it, but.
Yeah, no, thanks a lot for a very nice talk, Nori. So, if I understand, you gave a relation between the spectrum asymptotically and the question of whether or not the Krylov complexity would grow exponentially. And was that a criteria which is in general true or only in quantum mechanics? What is it? Because if it's a general fact, maybe you just check the asymptotic growth.
Okay, as I know, it's true in quantum mechanical system. In quantum field theory, not only the spectrum, but also the momentum that's contributing to the full spectrum. And usually this bothers our expectation. So what you said is more or less true in quantum mechanical system, but in quantum field theory, due to the momentum contribution, I think it changed. That's my understanding.
Just follow up on Raghu's question. In this case, what this Brownian kind of hitting is like n different particles, each of which I suppose hit with strength 1 over n, and n is taken to infinity. So in this limit, I would imagine that this Brownian motion sees just friction but no oscillations. And maybe that's why you see thermalization but no chaos.
Okay.
I just wanted to ask the connection of Krylov complexity with the notion of scrambling, because when you compute OTOC in a strongly coupled system, there arises the notion of a scrambling time actually that goes as temperature times the log of the entropy. What is the, do you have any thoughts about the connection between Krylov complexity and?
I think what is a scrambling, that's more or less associated to the OTOCs, and that's the nature of the 4-point function. But as I understand it, Krylov complexity you can completely determine from the 2-point function or its spectrum. So it's a 2 different diagnostic. And in order to see the scrambling effect or chaotic nature, I would say OTOC is a better quantity, as I understand it. So Krylov complexity look at some sub-different aspect, but not as good as OTOC or 4-point function. This is my understanding.
I asked because you talked about operator growth, which is somehow related to scrambling. That's why I asked.
Exactly. It's exponentially expanding, but only in the subset, not complete set. OTOC more or less see how the tiny effect keeps spreading to the complete Hilbert space. So in that sense, Krylov complexity look at only the subspace. That gives a difference. Does that answer your question? Exactly.
One question to follow up on Spenta. Did you try looking at circuit complexity in this model, and is it feasible?
State complexity.
Circuit complexity, yeah.
Circuit complexity.
Yeah.
Okay, I didn't study. That's
All right, if there are no more other questions, we can thank Nori again.